Hello everyone, this is Dr. Fan. I don't know if you have noticed, for certain ramps, if you apply a horizontal force, it does not matter how large your force is, the block would not move up. Why this is the case, we're gonna address this today. And if you are able to address this question by yourself, you should be able to solve all the ramp questions in AP Physics. Okay, now let's get into it. So let's assume there's a ramp here and we apply a horizontal force. How do we know if the block is gonna go up or not? Let's first do a free body diagram. We know there's gravity going down and there's normal force perpendicular to the ramp, and we have a horizontal force F going this way. In this case, there is also friction. So if we want to push the block up, then there's a friction force parallel to the ramp going down. So these are the forces we have. So I can construct my coordinate system along the ramp direction. So this is my positive x because I want to push the block up. And this is my y direction perpendicular to the ramp. So now I can get my net external force along both directions, sigma fx and sigma fy. But before I do that, I want to know the relationship between angle. So if this angle here is theta, we know this angle would be theta too. And because this force is applied horizontally, that means this force direction is parallel to the horizontal direction. That means this angle here is also theta. Now we know the angle relationship, we can do the force decomposition along both directions. So along x direction, I have a component from my applied force, which is this guy right here, which should be F times cosine theta. And then I have gravity's horizontal component going this way, opposing the motion, so I'm minus mg sine theta. And friction is also opposing the motion, so minus friction here. And because I want to push the block up, so this net force should be larger or equal to 0. Now along the y direction, I have normal force going up, and I have one component from the applied force, which is this guy, going to the opposite direction, which should be F times sine theta. I also have a component from gravity, which is this guy right here, opposing this normal force, so minus mg cosine theta. And I know there's no motion along the y direction, so along y direction the net force is 0. Let me label these two equations as equation 1 and equation 2. From equation 2, I know my normal force equals to Fn sine theta plus mg cosine theta, right? So I also know that from equation 1, my F cosine theta needs to be larger or equals to mg sine theta plus the friction force. If I want to push the block up, that means I need to overcome the static friction force. And I know my static friction force is smaller or equals to mu s times the normal force. Since I have my normal force here, I can find out the maximum static friction force, which is mu s times this whole thing. That is F times sine theta plus mg times cosine theta, right? So if I want to push the block up, remember, this is the criteria. So that means the force I need to apply should be larger than F times cosine theta, larger or equals to mg sine theta, then plus this maximum static friction force, which is mu s times F times sine theta plus mg times cosine theta. So now I can simplify this equation. So on left side, I got F times cosine theta. On the right side, I got mg sine theta plus mu s F sine theta plus mu s mg cosine theta. I want to move everything related to f on one side and the other stuff on the other side. So then I got f times cosine theta minus mu s times sine theta larger or equals to mg sine theta plus mu s times mg cosine theta. So this is what I get. So now we know this relationship, right? So this slide becomes a little bit busy. Let me go to the next page. So the key information we know from last page is f times cosine theta minus mu s times sine theta is larger or equals to mg sine theta plus mu s mg cosine theta. Then some student would say, okay, I divided the cosine theta minus mu s sine theta on both sides of the equation, so I get my f is larger or equals to mg sine theta plus mu s mg cosine theta divided by cosine theta minus mu s sine theta. So the student would say, as long as my force is larger than this value, then my block would move up, because that satisfied this criteria. So what's the problem here? The key thing is when you divide cosine theta minus mu s sine theta, you assume it is positive, then you get this force relationship. What if cosine theta minus mu s sine theta is smaller than 0? What does it mean? So if this whole quantity is smaller than 0, that means f has to be smaller than 0, because on the right side you got a positive value. But that's impossible, because if f is negative, that means f is going to the right. Then in that case, the block would not move up at all. So that does not make sense. In other words, if cosine theta minus mu s sine theta is smaller than 0, this equation here would not be valid under any force. No matter how large your force is, the block will not move up. And if we simplify this equation, we get cosine theta is smaller than mu s times sine theta. That means cosine theta over sine theta is smaller than mu s. That means cotangent theta is smaller than mu s. So how do we interpret this relationship here? We know when theta is from 0 to half pi. When theta is increasing, cotangent theta is decreasing. So when my angle is large enough, that make my cotangent theta may be smaller than mu s. And under that situation, it does not matter how large the force is, the block would not move up. This is kind of like a self-locking system. And if you consider the extreme situation, that is when theta equals to 90 degrees, that basically means the ramp becomes a vertical wall. So your block is here. In this case, it does not matter how large a horizontal force is, the block will not move up. If you understand what we have just discussed, you should be able to solve this question yourself. This is a pretty hard question for AP Physics, so if you can solve it, many of the AP questions related to ramp would be easy for you. I'm gonna leave this to you guys. Thank you. I will see you guys next time.